Hi folks, Dr. Gillies here. Today we're going to talk a little bit about taking chances for fun and profit as the textbook has identified. But what we're really going to be talking about is probability and why it's important to understand probability with relationship to our normal curve. We're going to be talking about several things here, and it's going to relate back to using our confidence interval. Right? We talked about confidence interval last week, and this week we're going to talk about why that's important to understand and how do we get to a confidence interval as far as a percentage of how confident are we that the results are either as a result of a treatment or there's an actual difference or that the relationship that we found is a real valid relationship versus one that just happened to come along, right? So join me as we investigate this particular element. Here's what we're going to be talking about, how probability relates to statistics and particularly to your studies, your thesis. That's going to be the important part. We'll talk about some of the characteristics of the normal curve, which you may have already had some experience with at the under other classes, right, with your data set classes. We'll talk about z-scores and what they actually mean. How do we interpret a z-score once we get one? And then we'll talk about how do we interpret the area under the normal curve for a given set of z-scores. So don't let the terminology scare you. We're going to take this step by step, and of course, I'm here anytime that you have questions. So the first thing we have to do is, why do we have to worry about probability in statistics, and particularly with relationship to our thesis, right? Well, we want to make sure that our thesis is providing crucial data and that we can either reject or not reject our null hypothesis, right? Remember last week we talked about the correct terminology of using either the null hypothesis and the alternate hypothesis and whether we can reject or not reject the null hypothesis. So probability, again, provides for a normal curve. Not all curves are normal, know that, but the closer we can get to a normal curve, the more accurate we can use probability to identify chances of the results not being within our control or being by chance, or that the study has not shown any true differences between populations or samples, or that our relationship is not really there. So it provides our understanding of a possible outcome, right? What's the possible outcome of something happening? It's also the degree of confidence that an outcome is actually true. As an example, are changes in student scores due to a particular intervention that took place or by chance alone? I've talked to you guys a couple times about it as an example, taking a pretest and a post-test for this class. If I give you the pretest and you score an 85%, and the average of the class ends up being an 87%, and then I give it to you again at the end of the class and you score a 95% on average for the class, is that really due to my teaching you statistics, or would that have happened no matter what, no matter whether we would have had that or not? And there are a couple of ways we can do that. One, of course, we might give you the test, provide you with the training, the class, give you the test again, and we could see if there's a difference there between the pretest and the post-test. Another way to do it might be to give you guys the pretest and give another class the pretest, but not give them the training, but give you the training, and then give you both the test again afterwards and see if there's a difference between your test and the test of those who did not take the class. So there's a couple of different ways that we want to evaluate that. And by using probability, we can determine what's the probability that it actually was as a result of the class or as a result of a relationship. So keep those things in mind. The normal curve, of course, has specific characteristics. Visual representation of a distribution of scores. Normally, again, the larger the sample size, the more you're going to get a bell-shaped curve. But there are three specific characteristics that we need to have for the normal curve, a normal distribution. One is that the mean, the median, and the mode are all exactly the same. It is also perfectly symmetrical about the mean. In other words, if you take the mean and you fold your distribution from one side on top of the other side, you're going to get an exact replica, right? Exact replica. The other thing is that the tails are quote-unquote asymptotic. That means the closer to the horizontal axis they get, but they never do touch that. They get really, really close, but they never do cross that horizontal axis. Here you can see some examples of what we're talking about here. It's symmetrical. If we were to split this right here in the middle and fold this side over to this side, we would get exactly the same results. It would look exactly the same. Notice that the tails don't touch on either end. And also note that it has a single peak and that the mean, the median, and the mode are all the same. Sometimes, again, we get events that occur in the middle of a distribution. We usually get a couple on each end. Again, the larger portion of people that we're going to get, whatever the might be, we're going to be in this area here. We might get not so smart people down here, and we get some very, very smart people up here. Remember, we talked about the IQ test and what the average IQ test should be. Well, the average IQ test is right here in the middle at 100, right? 100. And way out here, we have our outlier. It's the very, very smart people, our Sheldon Coopers of the world. And down over here, we have the not so smart people. So if you had a class and you had an average IQ of 110 over here, you can see that it's a little bit different from that element. And we get a little bit smaller probability that that's going to happen there as well. So that's how we can take a look at those scores and how they can be effective at looking at your models. Now, each one of the characteristics that you are going to find and collect data on from your population is going to have a curve. Whether it's normal or not has to deal with the overarching sample size as well as what the scores look like and how you develop your questions. The goal is to have a normal distribution, though, as I mentioned. The closer to a normal distribution we get, the more tools we have available to us to use. All normal distributions, again, between -3 and +3 normal standard deviations from the mean, right? So we can compare those. We can compare our distributions. Our class distribution of ages, if we had a large enough class size, can be compared with another class size. And we can see what the mean is for each one of them. And again, they're between different points on the x-axis, a certain percentage of cases will occur. This is a fact. This is the way that it is. You can identify clearly these particular ones. Now, this particular chart shows us what we call the empirical rule. This is our empirical rule. And the empirical, spelled E-M-P-I-R-I-C-A-L, rule, simply states that within one standard deviation on each side of the mean, right? Our mean is down here. Again, our peak, mean, median, and mode are right there. Within one standard deviation on each side of our mean is going to fall 68%, plus or minus, so about 68% of our total distribution. 95% will be between two standard deviations, and 99.7% will fall within 3 standard deviations. So that means you only have very small amounts that fall out here beyond 3 standard deviations. And if you think about it, this is where Six Sigma comes from in business practices. And we try and account for all waste within 3 standard deviations above and below the mean. 3 plus 3 equals 6, right? 6 standard deviations. So this is an example of our cases under the normal curve. And again, this is called the empirical rule. So how do we identify, let's say that our raw score was here, how do we identify what percentage of people should fall out to between the mean and 100 and, let's say, 12, right? Or whatever number we can come up with, right? So we want to find out what is the probability that we're going to find a score within this particular element here. That's where we come up with what we call our z-scores, right? Standard score measured in standard deviations, that the raw score differs from the mean of the distribution. So when we look at these symbols, we can see that we have our z-score here, right? And we have our x, and that is the value of whatever it is we're looking for. In our case, we talked about 112 IQ, right? And we subtract that from our mean, right? And our mean in this case was 100 for our IQ. So we subtract 111 minus our mean, gives us a score of 12. And then we would simply divide that by whatever our standard deviation is, and that will give us our z-score in standard deviations. And typically you're going to see values ranging between -3 to +3. If you get a z-score of 16, probably should go back and do your work again because you're not going to get a z-score that's quite that high. So z-scores are important to understand, right? So make sure you understand the z-scores and practice finding them using Excel, which we're going to talk about in a few minutes here. So z-scores below the mean mean they're negative, right? If you had a IQ score of 95, that's 5 below the mean of 100. So you'd have a, probably depending on what it is, minus 0.5 of a z-score. And those above are to the right of the mean. Those are called plus ones. It's the number of standard deviations from the mean. That's all we're doing is converting our values to standard deviations. And z-scores across different distributions can be comparable. So how do we accumulate our z-scores? Well, here's an example with Excel. Notice we have our scores over here. And we compute our standard deviations, and we ask Excel to compute our z-score. And it will provide us with those particular elements. And we can see that our mean, in this case, was 12. How do we know that? Because there's no difference between 12 and the z-score there. So a z-score of 0 means that it is exactly the mean. Notice that down here we have another 12, it is 0 as well, and yet another one. Notice that anything above 12 is going to have a positive number. 0.5 for 13, 14 is 1 standard deviation, and so forth. Any values that are less than 12, or our mean, have negative values. Minus 0.5 for 11, minus 1 for 10. So you can see that as we look at our normal distribution, our positive numbers, draw a normal distribution here for you. Our positive numbers are going to fall to the right of the mean for a z-score, and our negative numbers are going to fall to the left of the mean for our z-scores. So what do these z-scores actually mean? Again, they're the area that's covered between the mean and that value that represent a probability of getting that score. For instance, if our class was at a mean of 22 years of age, let's say we had 30 people in the class, we had a mean of 22, and somebody had an age of 25, I would want to be able to compute what the probability is of picking that person of 25. Let's look at it a different way. Let's say that we are looking at salaries, and the mean salary for our class is $1,000. We are representing the union of glass blowers, right? We blow glass figurines, and our salary on average is $1,000. So everybody's average is $1,000 when you take them all and put them in. Your salary is $1,200. So you want to find out what's the probability of, how many people, what's the percentage of people that I earn more money than? Well, you can use that using the z-score. You would simply compute out what that value is. If we had our normal distribution and we had our mean of $1,000 here, let's say we had a standard deviation of, put 1,000 here if I can draw. And so we had let's say we had a standard deviation of $100, right? So one standard deviation above is going to be $1,100, $1,200, and $1,300. So we are at the $1,200 range. So we want to find out what's the probability of anybody making more than us, right? So we would look at this number from here up. So we could identify what that's going to be. The example they use here, in a distribution with a mean of 50 and a standard deviation of 10, what is the probability that one score will be 70 or above? Well, first off, we know that it's above our mean, so it's already a positive number, right? It's going to be a plus number. Since our standard deviation is 10, how many standard deviations above 50 is 70? Well, you have to multiply 70 minus 50 is 20, divided by 10 is 2. So that's 2 standard deviations above the mean. So what's the probability that one score will be 70 or above? 70 or above meaning we're looking at that number, change colors here, this number here, 70, 2 standard deviations above or more, right? So we're only looking for that area to the right of that particular element. Notice that we have said will be 70 or more. Various ways of saying these problems. One might be 70 or above, which means that we're going to include 70. Or if we say more than 70, then we're not including 70. So be cautious when you see those word problems again, how they have a tendency to work out there. This is a table that you'll see in virtually every single textbook that's out there. Notice that we have our z-scores over here. We have the area between the mean and the z-score here. And each one of the z-scores are calculated all the way out. They have done it in 1/100ths of a z-score. So basically we have 100 scores that you can look at. And you can see the area between the mean and, let's say, getting back to our example of 2 standard deviations, we could go down here and find out 2 standard deviations is right here for a z-score. So the probability, the area between, if we draw our curve, the area between our mean and 2 standard deviations is 47.72, right? 47.72. There's our z-score there. So we said, well, what's the probability of somebody making more money than us? Well, we know that we're not worried about this area down here, so we'll add 50% because it's a symmetrical, right? It splits in half. So 50% lies above, 50% lies below. But we don't want to worry about that, about people below us, but we want to only worry about people above us. So we would have to add 50, this area here, plus the area that we found the curve under over here, 47.72, which gives us 97.72. Really hard to draw on a little finger pad. All right, so then we subtract that from 100 because all probabilities fall under the curve. So 100 minus 97.72 will give us a probability of 2.28%. So you are making more than 97% of everybody that's out there. Only 2.28% of the people that are working in the glassblowers union are making more money than you if you're making $1,200. So that way you can see how far out there they are. Why is this going to be helpful for us? Well, remember that our normal confidence interval is at 5%. So 5% confidence interval, if we back this all the way up looking at our 45, the closest thing to 45 here, because 50 plus 45 is 95, and we see it is 44.05, right? So that is 1.65 z-score. And that gives us our idea of 5%, right? 5%. 5% from 50, because you notice these only go up to 50, not up to 100, because all you got to do is add the other 50 to it, because they're symmetrical. This applies both sides, right? If this was a negative z-score, these numbers over here are going to be exactly the same, right? No matter if this is a positive or a negative sign on these z-scores here. So even if you have a negative z-score, you can still go to this table and find out what the probability of that cumulative area under the curve is going to be. So once we figure that out, again, you can identify those particular ones. Again, the z-score can help you. This table is, like I said, in every single stats textbook that you'll find, usually in the front cover, right? Usually in the front cover, because it's such a huge element. Standard deviations and the normal curve are absolutely enormous as far as getting you to understand the value of it. So again, the z-score really represents an extreme z-score before determining a factor that chance to produce that outcome. Z-scores are typically reserved for populations. We have another tool when we're talking about samples, and that is called the t-score or t-test. And we'll be talking about that again later on. All right, so give me a call if you have any questions at all. Drop me an email, and again, we'll have a couple more meetings before the class is over, so we'll make sure that we talk about those. We'll talk to you soon. Bye-bye.